This is the Trace3D proposal presentation. Trace3D is an integrated electromechanical 3D printer. So the core of the background of this project is that there are two processes, PCB design and fused deposition modeling, or FDM 3D printing, which are both really well understood and relatively cheap manufacturing methods. However, both have pretty substantial limitations. FDM parts are limited to static applications, and PCBs are relegated to flat profiles. So while individually, each of these offer increased access to mechanical and electrical prototyping tools, together, when you have electromechanical integration, design freedom is extremely limited. So after interacting with many stakeholders, including industry practitioners, university professors, and hobbyist makers, they indicated that reducing the limitations that electronics and PCBs impose on mechanical design is indeed a problem worth solving to increase engineering design freedom. So the core of our innovation is taking the best parts of 3D printing and the best parts of PCB designing and merging them into one comprehensive platform for integrated electromechanical 3D printing. Comparing the processes between the Trace3D development cycle and the traditional development cycle, you can see that there are far fewer steps involved with Trace3D. Traditionally, you would have to breadboard, design a PCB, wait for the PCB to be manufactured, design an enclosure, wait for that to be manufactured, and then assemble the whole thing together. But with Trace3D, you can breadboard your design, go directly to CAD, lay out everything together, and then bring it over to Trace3D for complete manufacturing in one step.
So with this core need of our stakeholders in mind, we had 6 initial directions that we explored for this project. These were electromechanical 3D printing, as mentioned, a dual extruder 3D printer with one nozzle used for plastic insulating material and the other used for conductive traces. The second was inkjet printing, which is printing circuits out of a traditional home computer printer. Flexible PCBs, which are printed circuit boards printed onto a flexible substrate that can be bent into different shapes. Fragmented PCBs, which would involve taking a traditional PCB, breaking into smaller pieces connected via wires, and placing those small pieces into natural openings in a mechanical design. Embedded PCBs, which would involve 3D printing half of an enclosure for a PCB, inserting the PCB manually, and then printing the second half on top. And finally, the status quo, normal PCBs, traditional printed circuit boards with traces and electrical components forming a circuit. So we scored these initial project directions across these 5 metrics: the geometric limitation that it imposes on the mechanical design, the number of independent manufacturing process needed to realize an electromechanical system, the reduction in the range of motion imposed by the solution, the ease of assembly of the mechanical and electrical parts, and the number of standalone parts that need to be assembled. And the clear winner here was electromechanical 3D printing. So we selected this for further research and stakeholder outreach.
And so here we have a little bit of a breakdown of our existing competition. We can see that there's some very traditional methods, such as traditional breadboarding and just ordering custom PCBs. There are some other two-dimensional PCB generation products, such as the Volterra V1 and the Bantam Tools PCB mill. And then there's some more advanced 3D PCB solutions that would be similar to our product. However, they cost, for the 2 industrial solutions, be the Optimec and the Dragonfly, about 2 orders of magnitude more than our solution would. And the Voxelate Developers Kit, while very expensive, is now discontinued as well, but considerably cheaper than the industrial solutions. Breaking this down into 2x2s to visualize the opportunity zone here, we see that there is a kind of large zone for rapid prototyping of PCB manufacturing, and that's something we would hope to fill with our electromechanical 3D printer. And then we also see that we have a much wider opportunity zone for an affordable electromechanical 3D printer, whereas all the 2D solutions are either more expensive or very basic, and all the 3D solutions are substantially more expensive.
So we did extensive stakeholder research with experts in fields spanning design, electronics, and manufacturing. We categorized these stakeholder interactions into 3 main groups. The first group being that we spoke to industry practitioners. From these interactions, we learned that our product is innovative and does not yet exist in the industry, but there is a need for it, as their primary concerns were lower cost and more beautiful design aesthetics. The next group we talked to was Penn professors and high school educators. From these groups, we found that our projects can allow students to create higher quality projects without the concerns of certain like rat's nests of jumper cables and poor soldering of wires. The last group we spoke to was directly to makers who frequent the maker spaces that we see as one of our main markets. From them, we found out that makers often don't use custom PCBs because it's too time consuming or expensive. So it leads to them having unorganized and messy breadboarding techniques. So we think that our product would really revolutionize this maker space. Lastly, we talked to the additive manufacturing subreddit community, and we also made maker surveys to talk to real people who we think could possibly use our product. And we got a lot of really positive responses from those interactions.
With this stakeholder information in mind, we were ready to develop some quantitative characteristics for our system. The first was that from the average of the responses from that survey, the respondents indicated that they would accept a material cost of 3.25 times the cost of standard plastic in a 3D printer. So that resulted in a target material variable cost of under $65 per kilogram. Also from our survey, about half of respondents expected a print speed of half the Ender 3 Pros, a typical 3D printer for makers. So that resulted in a target print speed of over 50 inches per minute. Additionally, we want a low resistivity from our conductive material, as this allows for thinner traces and less material use. So we made our characteristic the equivalent from the previously mentioned discontinued product, the Voxel 8. Also from our survey, 3/4 of respondents expected to spend under 15 minutes processing the part after the completed print. And over half of survey respondents were unlikely to buy the system at $2,000, and over half were likely to buy it at $500. So this showed us a strong sensitivity to fixed cost. And a key indicator of that for our system was the number of extruders. So we're aiming for 2 or fewer extruders. And finally, the extrusion temperature is a key measure of the power consumption and therefore variable cost per print. And stakeholders want to minimize these costs, and traditional plastic 3D printers extrude at around 200 to 250 degrees Celsius. So we are aiming to extrude at 250 degrees Celsius or lower. With these characteristics in mind, our down selection proceeded between 6 different materials with which to extrude our conductive traces, these being solder wire mixed with liquid flux, solder paste, copper paste, a silver colloid, and a custom material. So we found values for each of these 6 materials across those 6 quantitative stakeholder informed characteristics that were previously mentioned. And as shown here, solder wire was the winner. So we're proceeding with this material going forward, but we also note that solder wire with liquid flux and solder paste scored closely behind in 2nd and 3rd. So we're going to keep a flexible design such that we could pivot to either of these materials should further research and testing point us in that direction.
So the final form of Trace3D will ideally be an electromechanical platform for printing readily available insulative and conductive materials, with the goal of creating objects that have highly conductive traces within 3 dimensions instead of just 2D like a classical PCB. So by eliminating the traditional flat PCB, electronics will be able to be perfectly integrated into their mechanical counterparts, and ideally you can create low-cost, compact product footprints as a result. Some possible applications for Trace3D include robotics, quadcopters, testing setup enclosures, student projects, and education. In all of these cases, there are marked improvements that you could see between higher aesthetic quality, increased battery life for drones, for example, by minimizing weight of the chassis. You could have decreased footprint and build volumes for the enclosures. And for education specifically, it can also serve as a tool for young learners interested in engineering applications.
So moving on to some of the finer details of our project, we defined a few subsystems that were relevant for our system. The first of these was the frame, which will be either constructed from 8020 aluminum, or we will likely be retrofitting a existing 3D printer in order to keep our design simple. In terms of motors and mechatronics, we are considering NEMA 17 stepper motors and Actuonics microlinear actuator in order to translate the axes of our 3D printer. The extruders and cooling system will likely be depositing the eutectic tin lead solder alloy, but we are still considering other possible solutions, including lead-free solders as well as some low-temperature materials. We're also tentatively deciding to use the Olsen Ruby nozzle in order to extrude the solder, and we have some choice cooling fans which perform better than those which we use in our hypothetical calculations. Finally, the software we will be using will be a modified form of the open source slicer Ultimaker Cura, and we will be running firmware on our 3D printer of the modified version of the Marlin software. So moving on to how we see an actual user interacting with our system, beginning with an idea for a part, they will begin the mechanical and electrical analysis together. And at that point, they will both design the CAD as well as the trace design of the part. Moving on, our software will generate a G-code path, and the 3D printing will begin with a dual 3D printer. It will print both the mechanical as well as the electrical components at one time, finally leading to the final product. So we began the quantitative analysis for our system by first looking at a thermodynamic approach to our system. We modeled the two most important modes of heat transfer, those being the forced convection due to the fans in our cooling system, as well as the conductive heat transfer due to deposition of hot solder. We found that the time required to cool a unit length of solder was 1/200th of a second. On the next slide, we use that result in order to calculate the heat transfer to PLA from the solder. We found a temperature delta of 28.3 Kelvin over Celsius. And starting from the cooled ambient temperature of PLA of 25 degrees Celsius, we found that this temperature would approach the glass transition temperature of PLA, that being 57 degrees Celsius. In order to deal with this, we are planning to implement a stronger cooling system than that one used in our hypothetical calculations. And we are also still considering materials with a different glass transition temperature. So moving on, we looked at the trace resistivity of a typical crop per trace using some standard values of a length of 1 inch, 1 ounce copper thickness corresponding to 1.4 thou of an inch, and 6 thou inches width of the trace. With a 25 degrees Celsius ambient temperature, this led us to a resistance of 0.08 ohms. From this calculation, we decided to set a goal for our own system that we will be able to print a solder trace with a thickness times width of less than 12 times that of the copper trace, outlined above, that being due to the lower resistivity of the solder trace we'll be printing as a goal for our system. And we can easily and reliably measure this with a multimeter in order to confirm that characteristic.
So for the testing of our initial extruder mechanism, being the solder extruder mechanism, we're going to make a one-dimensional gantry that we're just going to have to test some particularly important metrics such as the speeds and feeds for running the solder deposition, the necessary trace width, how conductive the traces are, what temperature we should extrude at, and several other very important metrics that we need to kind of figure out before we implement it onto an actual 3-axis machine. In order to do this, as you can see, we have a very preliminary version of that 1-axis gantry. Those are ground rods in a drilled acrylic enclosure. And then to the right is just a very simple example of our 2x1 test coupon, which will be 3D printed on Ender 3 Pros and then installed on a yet to be designed adjustable Z height plate within the gantry itself. And that will be used to test different channel widths and other important metrics as well.
So as you can see from the Gantt chart on the left, we have a very full semester of designing and manufacturing ahead of us. By the end of the semester, we have 3 main deliverables we aim to complete. The first is the full preliminary system CAD. We want to develop the entirety of our CAD so that it gives us sufficient time to fabricate and redesign if anything is needed to be redesigned. The second of that is the fabrication of the extruder assembly. We have decided that that's probably going to be the most difficult aspect of our projects. We want to get that done early on to make sure that we can test its functionality. Lastly, we want to manufacture the 1D test gantry that Owen just discussed. We want to make sure that we can test this so that we can test that the extruder assembly is usable in this minimalist simple configuration. And the way that we are going to measure success of these deliverables is if they are actually usable and that all of our tests are successful. So in conclusion, we wanted to just summarize some of the most important aspects of this presentation. Our problem that we are trying to solve is that the integration process of mechanical and electrical components is often messy and restricts design freedom. By reducing the limitations caused by electrical components, we can reduce the cost and increase efficiency for our stakeholders. This problem leads us to our final system form, which is an electromechanical 3D printer that prints both insulative and conductive materials to create designs with conductive traces in 3D. And so by the end of the semester, we plan on finishing the preliminary CAD system, fabricating the extruder assembly, and designing and manufacturing a test gantry. Lastly, we would just like to thank our amazing advisors for all of the help that they've already given us, our faculty advisor, Mark Yim, and our technical advisors, Kevin Turner, Peter Bruno, Dustin Roberts, and Nick Miguel. And these are our references. And that was our presentation. Thank you.